Let us see what is the meaning of elastic constants. We already covered the types of strains, that is your normal strain, longitudinal, lateral and volumetric, and the shear strain. And we see that the normal strain will be able to change the dimensions of the cross section, and the shear strain will help to change the shape of the cross section, not the dimensions. Let us see what is the meaning of elastic constants. The elastic constants are of 4 types, and that they are E, that is the Young's modulus of rigidity or Young's modulus of elasticity, G is your modulus of rigidity, K bulk modulus, and mu is your Poisson ratio. So the elastic constants are used to determine strain theoretically, right? We have to know what is the value of strain when a externally applied load is there. Because of that some deformation is there, because of that some stress is there, and what is the value of strain. So we can say that the strain is equal to, any strain is equal to your stress upon elastic constant. Why theoretically? Because we know that the strain is the change of dimension upon original dimension, or the deformation upon your original dimensions. So during your stress testing, that is on the UTM machine, we are not able to calculate the length in your, that UTM machine will give the only values of stress, that is the load, and elastic constants are known. So you can calculate strain theoretically with the help of elastic constants, right? So if you want to calculate shear strain, that is shear stress upon your modulus of rigidity, that is G. Normal strain is equal to normal stress upon Young's modulus of elasticity, and volumetric strain is equal to volumetric stress upon your K, that is bulk modulus. So you can calculate the strain with the help of these elastic constants, and the elastic constants will give you the relationship between stress and strain. This is the relationship between stress and strain as per your Hooke's law. So if the material is your homogeneous and isotropic, we will see later on what is the meaning of homogeneous and isotropic. So if the material is your homogeneous and isotropic, the number of elastic constants are 4, that is E, G, K and mu, and out of these 4 elastic constants, 2 are independent, that is E and mu, that is Young's modulus of elasticity and Poisson ratio. These 2 are the independent elastic constants, and the rest 2 elastic constants, that is G and K, is dependent on the value of E and mu, right? We will see later on what is the relationship between these E, G and K and mu, and we know that for the homogeneous and isotropic material, the number of independent elastic constants are 2, that is E and mu, and 2 elastic constants are dependent upon these 2 values. In strength of material, we have 3 different kinds of material. One is your isotropic. This table is the material, and here it is number of independent elastic constants. If the material is your isotropic, then the number of independent elastic constants are 2. If the material is your orthotropic, then the number of independent elastic constants are 9. And if the material is anisotropic, then the number of independent elastic constants are 21. Right? We will see what is the meaning of these 3 types of material, how we can define isotropic, orthotropic and anisotropic material. First of all, let us say what is the meaning of homogeneous material. Right? We can say that a material is said to be a homogeneous material when it exhibits same elastic property at any point in a given direction. Right? On any point in a given direction, the elastic properties are same, then we say that that material is your homogeneous material. If you change the direction, the value of property will change, but at any one point or at any point in the material in a given direction, the value of your elastic constant will be same. So the elastic properties are independent of point. In case of homogeneous, elastic properties are independent of the point. Now I can say that suppose this material is a homogeneous material, and in this I am taking 3 points. Let us say we are discussing about these 3 points, right? And we are taking this as a x-axis, vertical is a y-axis, and this is a z-axis, right? We are assuming it x, y and z. So we can say if on these 3 points the value of elastic properties, if it is a homogeneous, then in one direction at any point the value of elastic constants are same. Suppose in the x direction, this is point 1, this is point 2 and this is point 3. I can say in x direction, let us say the property is your E1. Is E1. So at all the points the property in x direction it will be same, that is E1. Right? So the properties are independent of point. They are dependent on the directions. So I can say in x direction the value of property will be same. If I change the direction to the y, so I can say if in the y direction the value of property is E2, then at all the points the value of properties in y direction will be E2. Then it is a homogeneous material, E2. At any other direction, let us say in z direction, if the properties is E3, so at all the points the value of property in z direction is E3. Right? So we can say that this is a homogeneous material. It exhibits same elastic properties in a given direction at any point. So this is the meaning of homogeneous material. Next is your isotropic material. We can say that a material is said to be a isotropic material when it exhibits same elastic properties in any direction at a given point, right? At a given point in any direction the property value will be same. If you change the point, then the property will be changing, but at any direction the value of property will still remain same. So in this case you can say that elastic properties are independent of direction. Right? Elastic properties are not depending upon the direction. Suppose this material is your isotropic material, and we are again taking 3 points. This is point 1, this is point 2, and suppose this is point 3. So if I am saying let at point 1 the property value or the elastic properties value will be E1, so in all the directions the value will be same, that is E1. In all the direction at this point the value of property will be same, E1. In any direction the value of property will be E1. When you change the point, suppose we came to the point 2, the property value will be changing, but in any direction the value will be same, that is E2. Suppose the property value will be changing E2, so in all the direction the value will be same, that is E2. In all the direction the value will be E2. If I changing the point 3, so I am saying let us say at point 3 the property value will be E3, so in all the direction the value will be E3. right? In all the direction, the property value will be E3. So this type of material is known as the isotropic material, in which the elastic property is same in any direction at a given point. So in this, at a given point in any direction, and in this at a direction at any point in a given direction, and in this in all the direction at a point. So this is the meaning of isotropic material. Next is your homogeneous and isotropic material. We say that the homogeneous and isotropic material are those material if it exhibit same elastic properties at any point in any direction, right? At any point in any direction, if the value of property is same, so we can say that that kind of material is your homogeneous and isotropic. Suppose this is the material which is homogeneous and isotropic, and again we are taking point 1, this is point 2, and this is point 3 on this material. So we can say that at all the points, at all the direction, the value of property will be same. In all the direction, let us say the value of property is E. So at all the point, in all the direction, the value of property will be same, that is E. So this type of material is your homogeneous and isotropic. So we can say that for homogeneous and isotropic, the number of elastic constants are 4, out of which 2 are independent and 2 are dependent on the rest of the 2. Now we can say that in this case, for homogeneous, we should know properties at 2 points, right? Because in homogeneous, we should know the properties at 2 points minimum, but for the isotropic material, we should know the properties at 2 directions. If in the 2 direction at any point, the properties are same, so we can say that material is an isotropic material. And if we can say the properties at 2 points in a one direction is equal, then that material is the homogeneous material. And for homogeneous, the number of independent elastic properties are 2, that is E and mu. Right. Let us see what is the meaning of an isotropic material. A material is said to be an anisotropic material if it exhibit direction dependent properties, right? If the properties or elastic constants are depending upon the direction, that is in all the directions the elastic constants are different, then the material is said to be the anisotropic material, which is the reverse case of isotropic. So we can say that in isotropic material, at any one point the elastic properties are same in all the direction, but in anisotropic material the properties are dependent upon the directions, and in all the directions the properties are different. So that is the anisotropic material. So if I can, now next is your orthotropic material. A material is said to be an orthotropic if it exhibit different elastic properties in 3 orthogonal direction at a point. Orthogonal means perpendicular directions. So if I can say that if suppose this is a point and we have 3 perpendicular here, x, y and z. So in all the directions, in all the 3 perpendicular directions, that is x and this is y, in x, y or in z, in all the 3 perpendicular directions the properties are different. Suppose in x direction the properties is E1, in y direction the properties is E2, and in z direction the property is E3. So we can say in this case the elastic constants are different in the 3 orthogonal direction. So this is also a type of, you can say this is also a type of anisotropic material, right? Anisotropic material, because in anisotropic material the properties are different in different directions, so this is also a type of anisotropic material, right? So in this case, in the orthotropic material, we have total 4 elastic constants. We have total elastic constant, that is 12. In this case, total elastic constants are 12, right? How? In all the 3 directions we have 3 modulus of rigidity, we have 3 bulk modulus, 3 elastic modulus or Young's modulus, and 3 mu. We have these 12 elastic constants in the case of orthotropic material, and out of these 12, independent are 9, right? Independent elastic constants are 9. Out of 12, independent are 9. So these are the different types of material, that is homogeneous, isotropic, anisotropic, and orthotropic. In the strength of material discussions, we are taking an assumption that all the material are homogeneous and isotropic. This is the assumption of your strength of material, that the material which we are studying in strength of material is homogeneous and isotropic. We are not, in this course, we are not dealing with anisotropic and orthotropic materials. Now let us see what is the relationship between the elastic constants. We already see that in the case of homogeneous and isotropic material, two elastic constants, that is E and mu, are independent, and the two elastic constants, that is G and K, are dependent on the E and mu value. So what is the relationship between them? Let us see. We are not going to derive the relations, I am just writing the direct relations. The first relation is between E, G and mu is your E is equal to 2G into 1 plus mu. E is equal to 2G into 1 plus mu. What is the relationship between E, K and mu is E is equal to 3K into 1 minus 2 mu, right? E is equal to 3K into 1 minus 2 mu, and the relationship between E, K and G is your E is equal to, you have to learn this, E is equal to 9kg divided by 3k plus G. 9kg divided by 3k plus G. These are the 3 elastic constant relations, and we know that the values of all the elastic constants E, G, K and mu are positive, that is greater than or equal to 0. Right, or positive, not equal to 0, because every material has some elastic constants. So the value of all the elastic constants E, G, K and mu are always positive, they cannot be negative, and we say that mu will be greater than equal to 0. Mu will be greater than equal to 0. What is the value of mu? That is the lateral strain upon longitudinal strain. This is the value of, this is the formula of your mu, right? This is the formula of mu, and mu will be greater than equal to 0. So if there is a material that is cork is a material for which the value of mu will be 0. The value of mu will be 0 means the lateral strain will be 0. In the cork, the lateral strain will be 0, and rest of the materials, the value of mu will be greater than 0, right? So if I say that out of these values, if I just eliminate the things, that from this we can write G is equal to E upon 2 into 1 plus mu, right? and from here K is equal to E upon 3 into 1 minus 2 mu. So I am eliminating E and K in terms of E and mu, right? G and K in terms of E and mu. We say that in this relation, in this first relation, if mu is positive, mu is always positive, so G is always positive because there is a plus sign here. But in this relation, there is a minus sign here, so there may be a chance that K will become negative. But as we know that K is always positive, that means your value of 1 minus 2 mu will always be greater than equal to 0. Right, value of 1 minus 2 mu, this value must be greater than equal to 0. If this value will become less than 0 or negative, then K will be negative. But elastic constants cannot be negative. So from here you can say that mu should be less than or equal to 0.5. This is the maximum value of mu will be 0.5. Right, the value of Poisson ratio cannot be more than 0.5. If it is more than 0.5, then the elastic constant K will become negative. So the value of mu will be less than or equal to 0.5. So we can say that for all the engineering materials, the value of mu will be, for all the engineering materials, right, all the engineering materials, they may be metals, they may be non-metals, they may be anything, the value of mu will be greater than equal to 0 but less than equal to 1 by 2. For all the materials, engineering materials, the value of mu will be greater than equal to 0 but less than or equal to 1 by 2. But mostly we are dealing with your metals. So I can say that for metals, the value of mu, if I write here that for metals, if the material is metal, then the value of mu is lie between 1 by 4 and 1 by 3. Right, for metals the value of mu is in between 1 by 4 and 1 by 3. That is 0.25 to 0.33 will be the value of mu for metal. And if for any material in the engineering, the value of mu will be greater than equal to 0 for your cork, and it should be less than or equal to 0.5. We will see later on what is the meaning of mu equal to 0.5. How we can define a material whose value of Poisson ratio is 0.5. We will see it later. Now if we want to find what is the upper and lower limit of K and G, that is your bulk modulus and modulus of rigidity in terms of elastic constant. If you want to find out this, so for all the engineering materials, if I can say the lower limit of mu will be 0 and upper limit of mu will be 0.5. For all the engineering materials, the value of mu will be between 0 to 0.5. If you put the value of mu 0 here, right, this is 1 plus 0, 1, so the value of G will be E by 2. The value of G will be E by 2. If you put the value of mu as your 0.5 here, this is 1.5, so 2 into 1.5 is 3, so the value of G will be E by 3. So the value of G will be E by 3. If you want to find what is the value of K, so if you put the value of K mu 0 here, so the value of K will be E by 3, and if you put the value of K as mu as 0.5 here, so this denominator will be 0, so E by 0 is infinity. E by 0 is infinity. So I can say that for all the engineering materials, the value of G lies between E by 2 and E by 3, right? The lower value of G will be E by 3 and the higher value of G will be E by 2. So G will be greater than or equal to E by 3 but less than or equal to E by 2. So this is for engineering materials. For all the engineering materials, the value of G will lie between E by 3 and E by 2. And if you notice one thing here, that with the increase of mu, if I am increasing the value of mu, if you increase the value of mu, the value of G is decreasing. This is 0.5 of E and this is 0.33 of E. So the value of modulus of rigidity will decrease, and if you increase the value of mu here, this is at mu 0, this is at mu 0.5. If I increase the value of mu, the value of K is increasing. The value of K is increasing. This is for engineering materials. These data will be helpful for you in solving the objective type of question in GATE or in your engineering services exam, right? With the increase of Poisson ratio, the value of modulus rigidity is decreasing but the value of bulk modulus is increasing. So for metals, if I want to calculate what is the value of G and K in terms of mu, so for metals the minimum value of mu is 1 by 4 and the maximum value is 1 by 3. 1 by 4 and 1 by 3. If you put here 1 by 4, so the value of G will be your E 0.67 E. 0.67 E. You can solve it by putting value mu 1 by 4. If I put the value of mu as your 1 by 3 here, so you can write then the value of G will be, sorry, this is 0.4. This is 0.4 times E. So if I put the value of mu as 1 by 3 here, then the value of G will be 0.375 E. Right? The nature will be same. If you increase the value of mu, G is decreasing. If we go to the K, if you put the value of K here, mu here, 1 by 4, so this is 1 by 2. This is 1 minus 1 by 2, 1 by 2, this is 3 by 2, E upon 1.5, so this will be equal to 0.67 E. And if you put the value of mu here as 1 by 3, and so the value of for metals, K value will be equal to E. For metals, K will be equal to E. Right? So this is the relationship or the upper and lower limit of G and K. So we can say that for metals, generally for all the metals, your Young's modulus is always greater than, see in this case for all the metals, the value of Young's modulus is greater than K and K value is greater than G. You can see here the lower value of K is 0.67 E. But the higher value of G is 0.4, right? Lower value is 0.67, K's lower value is 0.67, but the higher value of G is 0.4. So we can say that at any case, K is greater than G and E is greater than K because the upper limit of K is E. So we can say that at any case, E will be greater than K and greater than G. And we know that G will always be less than or equal to E by 2. Why? Because if you put the value of mu here 0, then only this term will be 1. So the value of G will be E by 2. And apart from 0 value of mu, if you put any other value of mu here, then this term will be more than 2. So this G will be less than E by 2. Right, because this is something 1.05, 1.1, 1.2, anything. So we can say that this G will always be less than or equal to E by 2, always. But the value of K the value of K in this formula depends upon the value of mu. It depends upon the value of mu. So if I can say that if the value of mu is 1 by 3, the value of mu is 1 by 3, in this case the value of K is E. The value of K is E. And if you put the value of mu here less than 1 by 3, right? If I put the value of mu here less than 1 by 3, so let us put the value 1 by 4 here, right? I am putting the value 1 by 4 here. So this is 2 by 2, 2 by 4, 1 by 2, 1 minus 1 by 2 is your 1 minus 1 by 2, 1 by 2, this is 3 by 2. So this is E by 1.5, right? This is E upon 1.5 is equal to K. So you can say that E is equal to 1.5 times K. So if I put the value of mu less than 1 by 3, so in that case the Young's modulus is greater than the bulk modulus. In this case the Young's modulus is greater than the bulk modulus, right? And if I put 1 by 3 here, then both are equal. If I put the value of mu greater than 1 by 3, right? If I put the value mu greater than 1 by 3, let us suppose we are putting the value mu is equal to 1 by 2. 1 by 2. So in that case, K will be infinity. K will be infinity. So at the value of mu greater than 1 by 3, your K is greater than E. K is greater than E. So we can say that the modulus of rigidity is always less than the half of Young's modulus, but the value of bulk modulus can be greater than Young's modulus, can be equal to Young's modulus, or can be less than Young's modulus. It all depends upon the value of mu. So these all relations will help you in the solving the objective type of questions. And we can say that for non-metals, for any non-metal, the relationship will be that your K will be greater than E and it will be greater than G. We are not discussing the non-metals in our case, just we are saying that in this case your K will be greater than E and E will be greater than G for all values of mu. For all values of mu. Right, for non-metals the value of this relation is not depending upon the mu, but for metals the value of E and K is depending upon the mu value. So this is the relationships between E, G and K and mu. You have to learn these three relations. Right, stop.